All right, guys. Thanks for having me here. Let's see. So I'm going to start out with just a quick background of where I'm coming from. I was in these seats much like some of you are here today. In fact, I think I was on SCPD for many years as well, so I don't know if I'm going to get like the voice of God coming in if someone asks a question. That's always fun. And so I'm going to give you my path coming here, and this is kind of a fun little thing. When I was a small child, I loved computers. I had a little Commodore 64, I had an Amiga, I had a 286, a 386, a 486, a Pentium Pro. I was really proud of this. I decided, you know what, I want to go into computers. So finished up in 2001 here, had a Bachelor of Science in Electrical Engineering. I got a Master's in 2004 while I was working over at Intel. And so I decided, I love these computers, I'm going to design them. So I started working in the Itanium division, so the enterprise processor division, where I was working on the Madison and Montecito processor, which at the time was the largest chip in the world, billion transistors. I guess there's 2 billion in the latest iPhone, so it doesn't mean much anymore, but at the time it was really big. And then it was a 4-year, 300 people project. That was for a processor shrink. It was not a new processor. And how about one of these x86 processors that people are using these days? One in this laptop. Well, even at the time, it was over 1,000 people. I was a very small cog in a very, very large machine. Itanium didn't do so well. I knew many people, including all of the press, which called it the Itanic. If you'll notice, we have the sales forecasts in blue, and as each year went along, they revised the sales forecast repeatedly and repeatedly, and the actual, well, it didn't quite match. So while they weren't doing so well, and it becomes, well, the big picture matters. So here I was working over at Intel. Projects failing, life is very nonlinear. 98, they laid off 5,000, 2006, they laid off 10% of their workforce, 2014, another 5% of their workforce. It just kept on going and going and going. And they were outsourcing the people over here, they're moving it to Taiwan, to India. It's a fantastic company, by the way. I have no problem with what they were doing. It's just they had to do these. These were the market forces. In semiconductors, the design costs were greatly increasing. So number of projects going down, costs just spiraling up. I don't think any of that's changed. It's just, this is what I was trained for. This is why I was an electrical engineer. And I could see that there's a lot of problems with the whole field. It's a difficult field. It's shrinking in some sense and growing at the same time. I've been talking to a lot of people in the chip industry, and they feel like we're hitting peak semiconductor in some sense. It's a huge part of what runs the world, but nevertheless, it's not growing in the same rate that it was when I was a kid. So I also want to build stuff. I want to invent things. So 2004, I'm going to change. I could go to medical school, I could go more graduate school, go to business school. So I decided that all of those options, I wanted to end up in the healthcare field of some sort. Healthcare seems to be growing pretty rapidly. It's very interesting, as I have a lot of personal connections to it. It's something that I very much enjoy. So grad school, as all of you guys here right now, is a great place to reinvent oneself. So I worked at Berkeley from 2004 to 2010 as a graduate student, starting a new project, which I'll tell you about. Then I was a research scientist, and I was running a small lab over there with a fantastic PI from 2010 to 2014. And finally, in 2012, I started up this company, Magnetic Insight. Got funded in about 2014, and now we here are in 2017. So a bit about spinning out the company. Well, I'll be honest, in 2012, I was burned out. It had been a very brutal few years. Personal stuff happened. My wife passed away, and I was just done. I was out. So I started shopping the technology around. I'm like, you know, I can't do this right now. So maybe I can get this technology out. I mean, here we are. I'm 8 or 9 years in developing something. I just want the world to see it. I don't want it to be stuck in some lab somewhere where no one ever sees the technology. So I found a CEO. This was completely happenstance. So here's Anna. Here, I'll get her picture up here. It was completely happenstance. I tried to shop this out to a number of companies, and the leading sales leader in small animal imaging, and I'll explain what we're doing in a little bit, is a company called Perkin-Elmer. And Perkin-Elmer is a multi-billion-dollar company, and we got the technology into their hands, just an overview of what it could do. And Anna came to us and said, hey, you know, we absolutely love the technology, but Perkin-Elmer, we don't develop new stuff. It's not far enough for us to license it in and start shipping product out. We expect that to happen immediately. We can't build up a design team. In fact, I don't think they even have any design teams. So where do I go with that? Well, it turns out that she was going through some personal changes too. So her career was at Caliper, and then Perkin-Elmer had bought Caliper. Perkin-Elmer is a Bay Area company, and so she was here in the Bay Area, Perkins over in Massachusetts, and so she'd been flying back and forth and commuting to a job in Massachusetts. So she's like, well, hey, why don't we just spin this out into a company? Maybe Perkin-Elmer will buy it later, who knows? We could bring it quite far. So that's how I found a CEO. She quit her job, joined the company, and all of that happened in the course of just a couple months. It was just it's all just happenstance. Didn't expect that to happen. So here we go, starting the company, and the company is Magnetic Insight. So what we develop is called magnetic particle imaging. So a little bit of history just about medical imaging. I don't know if people here have medical imaging backgrounds, but I kind of want to bring you into the fold a little bit. So medical imaging, we've all heard about the things that we can do. It's really revolutionized how we do medicine. So we use it for screening. We use it for the primary diagnosis. We do treatment planning with it. And we finally monitor how well those treatments performed. We've got, on this page, we've got, let's see, that's I think that's an MRI, here's a mammography, here's another MRI, nuclear medicine, a CT. These are all these different things that you've heard about. You've probably seen it on, I don't know, Grey's Anatomy, or I don't know what people watch these days. But it's an important part of medicine. And there's really two types of medical imaging. Even though we have all of these different specific technologies, we can break it down a little bit further, more granular. And we have anatomic imaging, and we have molecular imaging. So anatomic, we only see anatomy. We use what's known as a contrast agent, something that you inject, changes the color a little bit. And finally, what that contrast agent does is it enhances how the image looks. It changes its conspicuity, which is a fancy word for it, changes its contrast and how well you can see things. And the contrast agents are at the millimolar to micromolar range, primarily at the millimolar, and that's what we see in MRI and CT. A whole nother type of medical imaging is molecular imaging. We don't see anatomy. So I forgot to give you some examples of anatomic. That's MRI, that's CT, that's ultrasound. That's the dominant ones there. So molecular imaging, we see a tracer. So a tracer is something that it shows a function, so it shows it doing something. We don't see the anatomy at all. So for example, in nuclear medicine, we'll give an injection of a tracer that will see a cancer, that will make it light up, but you don't see the rest of the body. All you see is, actually you'll see the bladder, and then you'll see a cancer, and you'll see a few other things, like things of high activity, maybe bone, brain, etc. But we don't see tissue. Now what we can do is we can combine the two. So here we have something that sees function, nuclear medicine, PET, SPECT, and then we'll combine it with the CT scan so we can see where it is in context in the rest of the body. So molecular imaging and anatomic imaging, there's a huge gulf between the two, but we can bring them together. These techniques are all built on different principles, whether it be optical attenuation, magnetic resonance, sound reflection, or nuclear decay. We have 4 different ways of seeing into the body. 3 of them are anatomic, and 1 of them is molecular. So all of these different properties lead to anatomic imaging, and again, over here is molecular. So now I get to introduce what we do. So we use what's known as magnetic particle imaging. which is a molecular imaging technique. We don't see tissue. So what we can see is an iron oxide tracer. We unambiguously say, here's an iron oxide, where is it in the body, how much is in there? And something to remember is MPI and MRI, even though the names are pretty similar, have nothing to do with each other. We can't get an MPI scan on an MRI machine. So we do preclinical and clinical imaging. What we have right now, the physical system that we have produced, is for preclinical. So I'm going to talk about what we can use this preclinical machine for. But when you're listening to this, keep in mind how we might translate these very ideas into imaging people, which we'll be doing in the next couple of years. So here on the left, we have an MPI and a CT overlaid. What we have is we've implanted little iron oxide tracer bundles into this animal. And you see on this animal, we can tell that there's the same amount of tracer under the skin right over here. We've also labeled these same tracer vials with an optical tracer. And the optical tracer, if you notice, the signal changes dramatically as we drop deeper into the tissue. It turns out optical imaging is the dominant preclinical imaging technique, but we don't use it in the clinic because we can't see deep into tissue. Person here, but my head is 10 centimeters to the middle, another 10 centimeters all the way to the other end, and here I can't even image 2 millimeters deep, so we don't use optical clinically. And finally, here's an MRI and it turns out all of these, even though they look very different, are of the same animal. So here we have 2 tracers implanted. Optically, we can see that there's 2 different groups of tracer, although we can't really tell how much there is. And MRI, well, it turns out people will say MRI sees iron oxide. Well, it technically does, but it really can't quantitate it. And here, this is the difference between an anatomic imaging technique and a molecular imaging technique. I can't tell how much is there. In fact, I can't even really find it unless I knew where I put it. So it's just they're different classes again. So we can see through deep tissue. So for example, here we have MPI going further and further into tissue, whereas in optical, the signal drops very dramatically. We can see that the optical signal drops exponentially, which is it's because of Beer-Lambert's law. So it goes down exponentially, whereas MPI, the signal, we could image through a human with no problem. We've used the technique for a number of applications in small animals. We can do cell tracking. I'll talk more about this one in a little bit. We can do blood pool imaging, where we're seeing how the tracer is flowing through the blood in real time. We can also do, different types of blood pool imaging. Here's TBI imaging, for example. But before we get there, let's talk about how it works. Because we're an engineering group here, and I would love to show you, well, physically what's happening. So suppose we have 2 magnets. These magnets are pointing at each other. So you have the North Pole and the North Pole pointing to each other. The 2 magnets are pushing away. And we get these field lines that go through here. And this, coming back to Maxwell's equations, well, the field lines diverge. If this were an MRI, the field lines would go straight. This is the main magnetic field. This is the primary thing in the middle of that magnet. And it's completely different than what we do with existing techniques. At the very middle of that magnetic field, we have what's called the field-free point. The field-free point is where the magnetic field passes through 0. And I'll show you a little bit more about how that works in a little bit. So let's just take a closer look at that field-free point. And the way that we produce a signal is when we take that field-free point and we rapidly translate it across an animal or a patient, it produces a signal. And the way it produces a signal, this is a nanoparticle right here. And this nanoparticle will tend to point at the field-free point. And as we transition the nanoparticle, or the field-free point over the nanoparticle, the particle will flip to follow the field-free point, and it'll induce a signal blip in a receiver coil, which is shown in green over here. And then we have a little preamplifier on the receiver coil. So nothing too special there. So a little bit more in depth, if this right here is the field-free point, and this right here is the nanoparticle, as the field-free point transitions over the nanoparticle, we're going to see that that particle remains aligned with the magnetic field lines. That's actually what's happening. And it's going from a positive magnetization to a negative magnetization, flipping in the middle. And as we flip in the middle there, we detect dm/dt, the change in magnetization over time, and that right there is a signal blip. And that's the point spread function of the system. If we have a point source in, we get a point source image out. Let's see what happens when we have multiple particles. Again, here's the field-free point. The field-free point, we're going to transition over these nanoparticles, and the nanoparticles, one at a time, flip to follow the the local magnetic field, and they flip, 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 flip. We go from a positive magnetization to a negative magnetization. We detect dMdt over there, and there's our signal. So in this case, we have a rect in, and we get a rect out. Pretty straightforward, right? So fundamentally, what's happening is if we have an animal, we have a field-free point, we transition the field-free point across the animal. Let's see that happen. And then we'll get sort of a characteristic image. And so this particular animal was injected with the liver targeting tracer, and it's gone into the liver. So you see the liver, and you also see the spleen. And it's overlaid on the CT. So the multi-core nanoparticles are the type of nanoparticles that we see. So multi-core as well as single core. And I'll show you these two different classes that we can image. This particular class of particles, there's commercial examples, and most notably one called Resivist, which is it's an MRI tracer, but it also produces a decent MPI signal. And it was first approved for human use in about 2001 in Europe, and is still currently used in Japan. So our company internally, we sell it as VivoTracks for preclinical use, in case any of you want any. Then there's a whole other classes of nanoparticles that we can see. So for example, there's these single core nanoparticles. And the MPI truly benefits from having cores that are customized to how MPI works. So so far, the best cores are about 20 to 25 nanometers, and these ones show up fantastically. We can get down to about 400 micron resolution. So the physics of how the technique works is the resolution is related to the volume of magnetic material in each core. So we can actually draw resolution curves in relation to how the gradient strength and the nanoparticle interact. So here, let me use my mouse here. So the nanoparticle, which is these contours, interact with the field gradient. And if we say have a 6 Tesla per meter gradient, which we've built, we get sub-millimeter resolution when we have a 30 nanometer particle. And so all of this plays out in actual, both in theory and in experiment. So this is a more engineering group. So usually I don't go through the hardware, but I can kind of go through what the instrumentation looks like. So we have a few basic steps to producing an MPI image. So first off, we have to produce a magnetic field. And so we produce either magnetic field-free point, or in our case, we typically make a field-free line. So it's that sensitive point. But instead of having a point where we're detecting the the nanoparticles, we extend that into a line, and just the volume of that line is so much larger than a point that our sensitivity goes up by about 2 orders of magnitude. So we'll produce one of these field-free points using 2 large magnets, and then we get those flux lines, and finally the field-free point in the middle. What we're going to do is we're going to take that field-free point, and we need to be able to slowly translate it across an animal. So we got to slowly translate it across an animal. The reason we need to slowly do that is because the change of magnetic field is so large that we can't rapidly do that. We're talking about a time-varying field of about 0.2 Tesla. We can buy MRI machines for humans that are 0.3 Tesla. So we are time-varying the strength of one of these lower field MRI magnets. It's a huge amount of power. We need to rapidly translate that field as well. So slow translation of this field-free point or field-free line does not produce a signal. We have to move that field-free point or field-free line at about 1,500 meters per second. We can only do that electronically. So we're going to shake it around real quick. And that's going to induce the signal or produce a signal from the nanoparticles. So we're going to receive it with a receiver coil. And finally, through a lot of image processing, we turn that signal into an image. So if this is the main magnet, there's a lot of other stuff going on. There's all sorts of filters and all sorts of other things that are happening within the machine. And I'm not going to really go over those because that could take another hour. But the complexity is something that's very important. Well, how complex is it? Well, we believe MPI is very comparable in complexity to MRI, but it's comparable in different ways. In MRI, the hardest thing to do is make that main magnet. Once you make the main magnet, there's a lot of other difficult things too, but one of the hardest engineering technical difficulties is producing something that's a part per million in accuracy. And the only way to do that is through a lot of patient engineering and probably about, I'm thinking, 30 years of physics research? So in contrast, MPI, we use part per million levels of harmonic distortion. So we're putting in, say, let's see, we're putting in about 6,000 watts of transmit power, and we're detecting something in the nanowatt range. So we have, I think it was like 16 orders of magnitude of power difference between the input and output, and we isolate that through very careful filtering. And so we have to have part per million levels of harmonic distortion to be able to make that work. And then finally, the costs are pretty comparable. We have shield rooms and all sorts of other stuff like that. So what can we use MPI for? We have a number of different applications that we're currently developing internally. And they range from cell tracking and tumor imaging and a few other ones. And I'm just going to go through cell tracking, tumor imaging, and blood pool imaging. And these other ones I'm not going to talk about. So this work was done over at UC Berkeley when I was still a researcher there with one of the smartest people I've met over the years, Dr. Zheng. And what we're going to do is we're going to demonstrate that using all of this crazy technology that we can track cells. Because it turns out there's no good techniques for tracking cells right now. So what we're going to do is we're going to start by labeling some mesenchymal stem cells, and then we're going to inject them and longitudinally follow them for about 12 days. So simple experiment. You start with cells, label them with Resivis, so that the iron oxide tracer that's approved for use in humans, and then we're going to inject these different animals and see what happens. So immediately after injection, here's something that's pretty cool. Cells go into the body, and guess what? They get stuck. They get stuck in the lungs. So it turns out we just built a $1 million lung imager, which is useful, it turns out. But here we can see the beautiful lungs over there of this rat. It's all in 3D. We can see what's happening there. But here's something that we cannot do with existing techniques is 12 days later, where did all this tracer go? So they're just not going to sit in the lungs because cells can move. Cells can squeeze through things. And there's no tracer technology out there right now that can last for 12 days. Except for this, because the inorganic nanoparticle, the body can break it down, but the body breakdown half-life is much longer than 12 days. We can actually extend it to as long as we want, and we can also shorten it if we want it to break down in 6 hours. So it's because it's an inorganic particle and we're detecting their magnetic nonlinearity. A control experiment would be like what happens when we just inject the tracer. So immediately after injection, we see it just goes to the liver over there. So we can also measure the post-mortem distribution. It's kind of like scintigraphy, where you take all the organs and lay them around and see what happens. And it also lasts for many months. So we've done the same experiment in the brain for about 3 months. And there's many applications for this. For example, if we're doing a Parkinson's treatment, we will implant cells as the Parkinson treatment. These are some of the research applications. And well, how many of those cells are alive? Are they in the right spot? Have they moved? All these sort of questions we can answer using this sort of technology. The signal is also very linear. I never put r squared of 1 because I don't know if that's technically possible, so I always end up having to go for many digits. And then with all of that, the most important thing, it turns out, is this next one. It's like, here's how other techniques do the same sort of cell tracking. So MPI, immediately after injection, we see it went to the lungs. It's pretty straightforward. Here's something that's from literature where people are tracking cells using optical imaging. And, well, they're in the lungs. And this is what people use the most in the research lab right now. It's just, this one is a pretty bulletproof way of doing it, but it's non-quantitative. It'll tell you it's in the lungs. But if you flip the animal over, the images look completely different. So it's very difficult to use. And finally, over there on SPECT actually has a pretty good picture of the lungs. The tracer only lasts for about 2 days, though. After that, the tracer half-life is just a radioactive decay, has gone far enough down that you just can't detect them anymore. So in summary, MPI is quite good at cell tracking. But that's not all that we can do. So what we're going to do here is another bread and butter imaging of medical imaging, which is seeing if people have cancer. So this is from a couple of fantastic students. Elaine's over at Berkeley still. Mindy just went over to MGH for her PhD. So what we're going to do is we're going to take a nude rat, so it's an immune-compromised rat, and implant a tumor, and it's going to grow this tumor, and then finally we're going to see where this particular tumor is. So here's the sort of images that we can get. Right here we see the rat. We're taking a slice right down the middle. And you see right over here we have this a tumor that's slowly collecting tracer over time. So immediately upon injection, you see that there's this ring enhancement. You see this ring around the tumor. And what that ring comes from is, so if we have a rapidly growing tumor, and you have this tumor, you have this network of blood cells, or sorry, blood capillaries around it. And so there's this blood volume. And if you take a slice through a ring, or sorry, the sphere, you get a ring. So that's why that ring is around there. Then over time, these nanoparticles are finding their way slowly into the tumor itself. And this is because these tumors can often have very leaky blood vessels. So these are two different effects that we're able to visualize here. If we take a look at the 6-hour time point, we can see this is when the most particles have found their way into the tumor. We can actually see the image across the entire animal. So here we can see this is the heart, the liver's over here, here's the spleen, and guess what? Tumor's over here. This is a different animal. And over the next few hours, we see that the tracer is being pulled out of the blood by the liver and the spleen, and the tumor is also pulling just a little bit of tracer out. And so that we believe this is about 2% of the total injected dose around inside the tumor. And so the dynamic range of the technique enables us to both see the liver as well as what's happening in that tumor, which is very remarkable for what we're able to do here. All of this is quantitative. So for example, if we wanted to say how much was in the tumor, we can say those sort of things. And quickly moving on here, this is a type of blood pool imaging that I'm talking about here. So when we're seeing into this blood coursing through the veins, through the tumor, well, what else can we do with sort of blood pool imaging like that? Well, let's just do a quick example. So what I'm going to do here is I'm going to take a standard normal animal, it's got nothing wrong with it, and I'm just going to inject and see what happens. So immediately after injection, it turns out that we can get a pretty nice picture of the brain. So we inject a tracer in. Remember, we don't see tissue. We only see tracer. So what we're seeing over here is tracer in tissue. We're seeing blood that's coursing through tissue at the capillary level. We can also see it, up different levels in the arteries and in the veins. So if you see over here, you see this ghostly outline. You can see the teeth over here. If you wait for that to turn around, turns out there's a lot of blood in the teeth. Didn't expect to be able to see that. We're starting to be able to label some of the internal arteries and veins, and then we can also see the external arteries and veins. So usually blood comes in on the inside of the brain and comes out on the outside. The moment that we're able to see blood, well, how about can we see changes in blood flow over time? So what we're going to do here is a different sort of experiment. We're going to give the body a stimulus and see if we can make the blood vessels change. So this is kind of like doing functional MRI or functional imaging. And so what we're going to do is we're going to give this animal, the same one actually, CO2. So carbon dioxide is a very potent vasodilator. And the reason it's a potent vasodilator is that's part of our body's regulatory system for when we think really hard, and then the blood vessels open up, more blood comes in, and that's a lot of what leads to, say, the bold stimulus or the bold effect in MRI, or in our case, this sort of effect. So what we're going to do is we're going to scan that slice on that animal repeatedly, scan over and over and over again, once every 8 seconds, which is it's at a good rate, but we should be getting a little bit faster in the near future. And we have 2 minutes of oxygen, then 4 minutes of a mixture of oxygen and CO2, and then finally back to pure oxygen. So we're able to start to see some of these different brain structures. So as the blood vessels open, we see that blood rushes in to the animal brain. And so to get everyone oriented, this is the animal brain. The trachea is over here. We got some ears up here. And we see the blood rushes into the very middle of the brain, but it's got to go somewhere. So you have all this extra blood coming in, and so up here we have a draining vein. So I don't know if you guys can see that over there. And so the blood sort of leaves the brain, and then we turn off the CO2, and everything goes back to normal. So there's a lot of different applications for this, and this is something that we've been slowly leading towards in clinical medicine, is, well, if we can do, say, for example, MRI, can we use fMRI, functional MRI, clinically? And right now, it's very difficult to use functional MRI clinically because the SNR is too low. Whereas something like this, the SNR is much higher, and we could quite possibly use it clinically. So I'm going to just change tracks and get back to some hardware because we have a lot of engineers in here. And so that was my brief foray into the biomedical world. But back to hardware, this is the system that we've built to do all of this. And this is the momentum imager. And this install right here is actually over just down the street over here in the Clark Center. And so this is the first time that it's left the laboratories over at UC Berkeley. And as part of the company, we commercialized this, built a commercial-ready product, and now we're testing it over here. Now, what's inside it? So I have the pretty outside, and usually I don't show this one, so I'm showing it just to you guys, and apparently everybody online. So this is what's inside. So the machine itself weighs about 4,000 pounds, actually it's about 5,000. 4,000 of it rotates, so it's got a mechanical rotation stage that spins this large magnet around. And let me show you what that looks like. So the animal goes in on the right, and then we spin the whole magnet around it to produce a signal. We got a robot chain at the left. This is all a RF shield box, so it's spinning the RF shield box around it so that we don't pick up any external interference. All of those blue and red lines are water cooling because we have a lot of power to do this. This is all on a laminated iron return, and it's straight out of high energy physics. We use a lot of the same manufacturers as the people who manufacture linear accelerators. So it's quite an ordeal to get all of this to work, but we've got it up and running. Here, let me give you a better tour of the different parts. Here, let's see. So here we go. So animal goes in right here, goes into the imaging center of the bore, which is right over here. You have these two magnets. Here's this is the, I guess, right magnet. This is the left magnet. And these are the water cooling lines. We run at like about, I think, 90 PSI. We've got the power lugs come in there, there's power over there, and all of that power is coming through this robot chain along with all the water. This is a copper box that extends all the way through here, and the reason we can have an open front is the entire thing is built around a waveguide, and so external interference can't make it into the center of the imaging bore. Now, the unfortunate part with having a waveguide is that we can't put anything metal in the front bore, like I can't put a single wire in because then it just conducts all the noise in. So everything up in the front is built of glass. So we have like ceramic rods and stuff over here to be able to have a long cantilever load out in the end without conducting any noise in. So that's the system. Let's see that rotating around again. There we go. Took a couple years. And that's running at about 1/5 speed. So when we run it at full speed, it should be able to do a rotation in about 3 seconds. So I think it uses like a 2 horsepower motor to spin it around. So what it looks like when we're trying to put it into place is it just takes power and water. This was a business decision as opposed to like ideally, if I could make any choice that I wanted, I'd run it with either a superconducting magnet or other thing that I can get to much higher fields. But as a business decision, we made it very simple to site. We use 480 volts and we use a lot of water. These are things that typical universities have, especially in their medical imaging. And it takes a pretty modest footprint, about 15 foot by 15 foot, so it would fit up here. In fact, when we installed it over at the Stanford site, this is a service corridor. So this is a service corridor for their MRI. So if they ever need to move their MRI, then we move ours into the hallway, they put the MRI out, and we put ours back in. We've written all of the software to do all of this, and we hide pretty much all the complexity. Our typical user is a biologist, and something that we've told our users, and something we very much believe, to use a system like this is very simple. It's to understand what's happening. It's like, you see the iron. That's what we can do. Now, I don't tell them how we see it, because if we got into the math, it's gonna blow their mind. But we have one click. It takes an image, gives it in a DICOM, and then they can like link it up with whatever they're working on. It's turned out to be wonderful. because we're also not having to support their use of the system because they understand you hit the button, you get where the iron is in the body. So what the user ends up seeing is they hit start and the robot goes in. The animal's at the end of the cantilever. And that's pretty much the user experience for most of this stuff. We're able to demonstratively show sub-millimeter resolution now. So with nanoparticles tailored to MPI, we're seeing down to about 400 micron resolution. So if we have 2 point sources getting closer and closer together, down to about 400 microns, we're able to resolve them. Turns out it's more difficult to get 2 point sources close to 400 microns apart than it is to actually image it. So the best we can get so far is about 600 micron spacing of our point sources. The signal is also completely linear. Again, we keep on doing these linearity tests to make sure that we haven't broken anything in the reconstruction. And we're linear over 4 orders of magnitude, which is very remarkable for medical imaging. It's not something that we typically see. We're also very sensitive. So here we are detecting particles in this vial that if you look in the light, there's absolutely no color in it. So here we are at about 10 micromolar of concentration. And for numbers, that's 550 picograms of iron per microliter. When we're talking picogram range, it's just, these are just minuscule trace amounts. We talk about, let's see, water contamination in nanograms. I mean, that's in per liter and stuff like that. So the SNR also scales down to as we get smaller and smaller vials. And so here's a vial that's roughly at the resolution limit of the system. Here we are about millimeter by a millimeter. And we have 1.1 nanograms of iron in here. And so when we're talking about nanograms of iron in a sample, and then we still see it with a decent SNR, so our detection limit is again in the picogram range. So that's firmly what we do in nuclear medicine, or in our case, MPI. So we're kind of getting into this very similar to other tracer imaging modalities. So anyhow, with that, I think I had 40 minutes, right? So here's a lot of the things that we do. And give me some questions, please. Yes?
So is your primary market going to be researchers or in hospitals for clinical use?
So this is when people talk about bootstrapping, this is not usually how they talk about bootstrapping, but this is our bootstrap market. So the technology in MPI is pretty complex, as you might guess. So we started in 2004, actually 2005. We started in 2005, and it took us until about 2014 to be ready to spin out the company. Over that time, me and my old PI, Stephen Connolly, who used to be here at Stanford for 20 years, we raised about 12 million from the NIH to get us to that spot. So here we spun it out, and we're like, well, to launch a clinical product, we'd have to raise 100 million. And that's the usual number that people bandy about. And it's pretty true. It might be a little bit more for capital equipment. But the preclinical research market, well, that one, in relative terms, is much smaller in terms of the capital requirements. So this is our bootstrap market. And all the technology that we've developed right now, to date, we're transitioning that into our clinical products. So all of the software, all of the control systems, all of the hardware is just going to get scaled up. It gets pretty big, though, but we had to get it working first. Yeah.
Was it difficult getting the necessary biomedical knowledge after a background in electrical engineering?
I would say I had very good training. So it was, as you guys are in grad school, it was all about my advisor. So he trained me. And so Steve, so he's been at Berkeley for, I guess, 12 years now. Before that, he was here at Stanford for, I think, 20 plus years. And he was working for Al Makovsky. So Al was one of the, I guess, just leaders in medical imaging. And so Steve was trained by Al. And so, by proxy, I mean, this is how this knowledge just gets passed along. And I can't say enough about my old advisor. Yeah. More questions? Yeah.
So you said it costs about $100 million usually to get one of these companies off the ground. Are you looking for like VC funding after you finish your bootstrap market, or?
Yes, yes, yes. We're headed down that path right now. Yeah. So we're able to raise much less money as well. So the whole idea behind a bootstrap market is that we have steady income coming in, and the steady income keeps us from, in VC parlance, keeps us from getting desperate. So we're building a true company for small animal imaging, and then we're going to just transition all that technology to the human side. But the amount of time it takes to build these things is just a different timeline than a lot of people are used to, just because they're so big. And so we just want to be safe on the way. Yeah.
You say you're 6 months into the selling cycle.
Mm-hmm.
Could you explain how you sell a machine like this?
Sure, sure. So the sales cycle is a very interesting one. So we're selling to researchers and scientists. So researchers at institutions like Stanford, and scientists at places like, I'm just picking a pharma company, for example, like Genentech, or a lot of these like people working on CAR T cells, and there's just a lot of pharma out there. So the typical sales cycle is it's a relationship sell. And so we know people, and our customers, our salespeople, we just have a lot of, we just see them as colleagues in the different institutions, and we're selling to people that we know and we care about. And hopefully they care about us too. But we're giving them something that enables a whole different field of research for them. Something that I believe they need a lot. And so we're selling it through relationship. We've got a couple sales guys right now, and that's just the typical sales process. So it's business to business sales. It's not, we're not spamming people sort of thing. We don't really cold call. It's a very involved one.
How much do one of these cost in cost for like a buyer?
Oh, so the sales cost is about $650,000, and that's about the price of I think a Lamborghini or something, right? So I put gold wing doors on it just because I could. Yes, it didn't. Here, I'll actually show you guys. So these pop up gold wings. I couldn't resist, but the sales cost is about $650K.
So when you started your PhD, did you actually think about this in the process, or did it just come along eventually, maybe in 2010 or 11, when you knew that it's going to happen? So
for a long time, I've been doing a lot of, and I don't know if you guys have done this one, a lot of business plan competitions, just because it's fun. So when I was here at Stanford, I think I did it, 3 times. When I went to Cal, I did a couple times. One time we won their whole business plan competition. But those were all different projects. It wasn't actually this project. This particular project, by the time that I was ready to commercialize it, I had totally burnt out. And so this one just kind of fell in my lap in some sense. But it was a whole career of working towards that spot to be ready for it.
So I was wondering, what is your life like as a CTO? What is your working focus? Where you see do some experiments in your company?
So that's a great question. So what's my life like in my position? Well, I'm in a tiny company, so most of the time I'm at a lab bench or building stuff or running around and trying to raise money. And as I continue to grow the company, me and the CEO were having to pull ourselves away a lot from the day-to-day of putting nuts to bolts, and try to do more the strategic direction. But I'm small enough right now that I still got have a lot of fun. But as we continue to grow, I'm going to get pulled more and more out of that.
what advice would you have for someone who's doing a PhD and is possibly interested in startups, but like we don't necessarily have the time to, in many ways, balance out or think about the bigger picture in our research, like in my case, for example? What advice would you have?
So what advice would I have for someone who's interested in this stuff but doesn't necessarily have the time for? So that's an interesting question. I don't know where to go with that one. It's more of a, I would say just keep it as a mindset. The way to either find your way into your own startup or to find your way into another group of people who are doing something together is just lots of talking. People are wonderful. And the interesting thing about startups is it's all just people. All of the people that we've pulled in and hired, it's all because they're a cultural fit. They have this wonderful background, and the only way that we run across them is just through friends of friends. The cold resume list seldom do much. It's all about people. Yeah. So I guess that would be my recommendation. Just talk to everyone. Anything else? Thank you. It was a 4-year, 300-people project. That was for a processor shrink. It was not a new processor. And how about one of these x86 processors that people are using these days? One in this laptop. Well, even at the time, it was over 1,000 people. I was a very small cog in a very, very large machine. Itanium didn't do so well. I knew many people, including all of the press, which called it the Itanic. If you'll notice, we have the sales forecasts in blue, and as each year went along, they revised the sales forecast repeatedly and repeatedly, and the actual, well, it didn't quite match. So while they weren't doing so well, and it becomes, well, the big picture matters. So here I was working over at Intel, projects failing, life is very nonlinear. 98, they laid off 5,000, 2006. They laid off 10% of their workforce, 2014, another 5% of their workforce. It just kept on going and going and going. And they were outsourcing the people over here. They're moving it to Taiwan, to India. It's a fantastic company, by the way. I have no problem with what they were doing. It's just they had to do these. These were the market forces. In semiconductors, the design costs were greatly increasing. So number of projects going down, costs just spiraling up. I don't think any of that's changed. It's just, this is what I was trained for. This is why I was an electrical engineer, and I could see that there's a lot of problems with the whole field. It's a difficult field. It's shrinking in some sense and growing at the same time. I've been talking to a lot of people in the chip industry, and they feel like we're hitting peak semiconductor in some sense. It's a huge part of what runs the world, but nevertheless, it's not growing in the same rate that it was when I was a kid. So I also want to build stuff. I want to invent things. So 2004, I'm going to change. I could go to medical school. I could go more graduate school, go to business school. So I decided that all of those options, I wanted to end up in the healthcare field of some sort. Healthcare seems to be growing pretty rapidly. It's very interesting, as I have a lot of personal connections to it. It's something that I very much enjoy. So grad school, as all of you guys here right now, is a great place to reinvent oneself. So I worked at Berkeley from 2004 to 2010 as a graduate student, starting a new project, which I'll tell you about. Then I was a research scientist, and I was running a small lab over there with a fantastic PI from 2010 to 2014. And finally, in 2012, I started up this company, Magnetic Insights. I don't think they even have any design teams. So where do I go with that? Well, it turns out that she was going through some personal changes too. So her career was at Caliper, and then Perkin-Elmer had bought Caliper. Perkin-Elmer was a Bay Area company, and so she was here in the Bay Area, Perkins over in Massachusetts, and so she'd been flying back and forth and commuting to a job in Massachusetts. So she's like, well, hey, why don't we just spin this out into a company? Maybe Perkin-Elmer will buy it later, who knows? We could bring it quite far. So that's how I found a CEO. She quit her job, joined the company, and all of that happened in the course of just a couple months. It was just it's all just happenstance. Didn't expect that to happen. So here we go, starting the company, and the company is Magnetic Insight. So what we develop is called magnetic particle imaging. So a little bit of history just about medical imaging. I don't know if people here have medical imaging backgrounds, but I kind of want to bring you into the fold a little bit. So medical imaging, we've all heard about the things that we can do. It's really revolutionized how we do medicine. So we use it for screening, we use it for the primary diagnosis, we do treatment planning with it, and we finally monitor how well those treatments performed. We've got, on this page, we've got, let's see, that's I think that's an MRI, here's a mammography, here's another MRI, nuclear medicine, a CT. These are all these different things that you've heard about. You've probably seen it on, I don't know, Grey's Anatomy, or I don't know what people watch these days. But all right, guys, thanks for having me here. Let's see. So I'm going to start out with just a quick background of where I'm coming from. I was in these seats much like some of you are here today. In fact, I think I was on SCPD for many years as well, so I don't know if I'm going to get like the voice of God coming in if someone asks a question. That's always fun. And so I'm going to give you my path coming here, and this is kind of a fun little thing. When I was a small child, I loved computers. I had a little Commodore 64, I had an Amiga, I had a 286, a 386, a 486, a Pentium Pro. I was really proud of this. I decided, you know what, I want to go into computers. So finished up in 2001 here, had a Bachelor of Science in Electrical Engineering. I got a Master's in 2004 while I was working over at Intel. And so I decided, I love these computers, I'm going to design them. So I started working in the Itanium division, so the enterprise processor division, where I was working on the Madison and Montecito processor, which at the time was the largest chip in the world, billion transistors. I guess there's 2 billion in the latest iPhone, so it doesn't mean much anymore, but at the time it was really big. And then site got funded in about 2014, and now we here are in 2017. So a bit about spinning out the company. Well, I'll be honest, in 2012, I was burned out. It had been a very brutal few years. Personal stuff happened. My wife passed away, and I was just done. I was out. So I started shopping the technology around. I'm like, you know, I can't do this right now. So maybe I can get this technology out. I mean, here we are. I'm 8 or 9 years in developing something. I just want the world to see it. I don't want it to be stuck in some lab somewhere where no one ever sees the technology. So I found a CEO. This was completely happenstance. So here's Anna. Here, I'll get her picture up here. It was completely happenstance. I tried to shop this out to a number of companies, and the leading sales leader in small animal imaging, and I'll explain what we're doing in a little bit, is a company called Perkin-Elmer. And Perkin-Elmer is a multi-billion-dollar company. And we got the technology into their hands, just an overview of what it could do. And Anna came to us and said, hey, you know, we absolutely love the technology, but Perkin-Elmer, we don't develop new stuff. It's not far enough for us to license it in and start shipping product out. We expect that to happen immediately. We can't build up a design team. In fact,